You researched the best caching system, built it, and shipped it. Congratulations, you're saving on computation power. You're just paying for it in storage. Einstein would have taken one look at your infrastructure and say you just EMC squared it. And once you catch that pattern, you'll see it every time you optimize. You may have heard of conservation of energy. Energy can't be created or destroyed, only converted from one form to another. I've covered this law and its implications in a previous video. You can check it out. Einstein's E equals mc squared takes that same rule and pushes it further. Mass is just another form of energy. Energy that's just very, very compacted. Same concept, just another mind-boggling angle. Look at the equation. Energy equals mass times the speed of light squared. The speed of light is already an enormous number, and we're squaring it. What Einstein shows us is that a very small amount of mass ends up equaling a huge amount of energy. That's exactly why nuclear reactions release so much energy from so little fuel. Barely any mass is being converted, but C² makes sure that the payout is massive. Look at the sun. Every second, it fuses hydrogen into helium, and the helium that comes out weighs very slightly less than the hydrogen that went in. The missing mass didn't disappear. It shows up on the other side of the equation as the light and heat pouring out across the solar system. Nothing vanished, it just changed sides. And that very slightly less mass is doing a lot of work. We're talking a sliver of a percent of a mass. And C² turns that sliver into enough light and heat to reach every planet in the solar system. And this runs in both directions. At the LHC, physicists send particles smashing into each other at nearly the speed of light. And out of that collision, brand new particles show up. Heavier ones. Ones that weren't there a moment ago. That's raw energy from the kinetic and impact condensing into mass. Matter out of pure energy. And because the exchange rate runs so steep, it takes a staggering amount of energy to conjure up even a little bit of mass. Same equation, same balance, just running the other way. Here's the thing about the word optimization. It sounds like subtraction, like the cost just disappears. It doesn't. It converts. Same equation as the sun. You're just trading in different currencies. But here's the question that actually matters. Which side of that equation are you on? The sun's side is a tiny cost buying an enormous return, a sliver of mass, an entire solar system's worth of light. The LHC side is the opposite, a staggering amount of energy spent to conjure up barely any mass at all. Same physics, wildly different deal. Actually, I added a caching layer and lowered the compute cost. Like, a lot. It's basically nothing now. Basically nothing isn't gone. Whatever's left showed up somewhere else. In your storage, in the hours someone spent writing the smarter version, in the complexity you now have to maintain. You didn't delete the cost, you moved it. Okay, fine, but storage is way cheaper than compute anyway, so it's effectively gone. Semantics. Maybe, but that's not actually the test. The test isn't whether you converted. You always convert. That part is not optional. The test is which side of the equation did you land on? Did you spend a little to get back a lot, the sun's deal? Or did you spend a lot to get back almost nothing, the LHC deal? Caching is compute converting into storage. And it's usually a fantastic trade. Tiny cost, massive payoff. One cached value gets reused 1,000,000 times. So a small flat storage cost buys back compute savings that scale with your traffic. Unless your traffic doesn't cooperate. High miss rates. Requests that barely repeat. And suddenly you've built and maintained an entire caching layer for a payoff nobody's caching in. The physics doesn't care what you expect going in. It only cares what your system actually does. A cleverer algorithm is CPU converting into dev time. And here, which side you're on depends entirely on scale. Spend a few hours turning an O(n)² approach into an O(n log n) one, and on a small data set, that's basically the LHC deal. Real effort, return too small to notice. but let the data grow and the same few hours flips into the sun's deal. The return compounds and start dwarfing what you spent to get it. And once you got that pattern, you start seeing it everywhere. Precomputing trades latency for storage and complexity. Batching trades responsiveness for throughput. Same equation every time. The only thing you actually control is which direction you run it in, and whether the direction is worth running at all. The conversion isn't optional. That part always happens. What you get back for it is the only part that's actually in your hands. The question isn't, how do I optimize this? It's, when I make this trade, do I actually come out ahead? Step 1 is naming the trade. Compute for storage. CPU for dev time, latency for complexity. If you can't say what you're paying with, you haven't found the win yet. You've just hidden the cost. Step 2 is the one people skip. Size it. A correctly named conversion can still be a bad trade. 3 engineering days to shave 2% off a job nobody's waiting on? That's dev time for compute, honestly labeled. Real cost for a return too small to matter. That's not a mistake in the math, it's just a bad trade. Because here's the whole thing in one sentence. You're always investing something. Sometimes that tiny investment comes back as an explosion of value. And sometimes a massive investment comes back as a scatter. Barely anything you can point to. So the real gut check isn't just who pays this. It's who pays this, and is what we get back actually worth what we paid? Because there's no such thing as a free optimization. And there's no such thing as an automatically worthwhile one either. There's only the trade you can afford, and, separately, the trade that's actually worth making. And if you like this kind of pattern matching, physics rules showing up the way that we build software, there's more of it right here. Next time you ship an optimization, think about what Einstein would say. Are you the E or the MC squared?